Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 10 on more structure work. So what we're going to really be focusing on today is trying to see this structure in a given algebraic expression and take advantage of the structure in order to rewrite the expression in different ways. Well, that's kind of vague, so let's jump right into it and see what I'm getting at. All right, here we go. Seeing structure. There's many times in algebra where we want to understand the larger structure of an expression. It's key to be able to treat parts of an expression as a single entity when it makes sense. When it makes sense. A lot of times it doesn't make sense, but sometimes it does. So let's take a look at exercise number 1 and see what I mean by that. Here we go. Consider the somewhat complex expression x times the quantity x plus 4 plus 2 times the quantity x plus 4. Letter A, write an equivalent trinomial expression, test the equivalency with a value of x equals 1, show the test. All right, so a trinomial, remember, is something that has 3 terms. So what I'd like you to do is I'd like you to pause the video and distribute that x through that x plus 4, distribute that 2 through the x plus 4, combine like terms, get a final trinomial, and then maybe we'll go through the equivalency test together. Pause the video now and go ahead and do that algebraic manipulation. All right, so let's do it. I'm going to write down the original expression just so that we've kind of got it a little bit bigger here. X times x plus 4 plus 2 times x plus 4. Okay, I can distribute that x. X times x is x squared. X times 4 is 4x plus 2 times x is 2x. 2 times 4 is 8. Notice I've got these like terms. So I'll get x squared plus 6x plus 8. I want to go back to a little piece of terminology, trinomial, right? A trinomial is a polynomial, or it's an expression that has 3 terms. One term is x squared, one term is 6x, one term is 8. Often trinomials that we work with in Algebra 1 will have what's called a quadratic term. That's a term raised to the 2nd power. A term that's raised to the 1st power, that's what's called a linear term, and then a term that has no variable on it at all, that's called a constant term. Okay, so 1, 2, 3. Now we can test again to see if this trinomial is equivalent to this by grabbing some random value of x. I'm suggesting x equals 1 here because it's easy to work with, and test the value of both expressions. So let's go ahead and do that. All right. We don't have a lot of room here, which was my error. I think I'm going to do that test up here and then I'll erase it. So if I test the original, actually, I'll just extend the page, give myself a little more room. All right, so my original expression, which I'll write down here in a second, was x times x plus 4 plus 2 times x plus 4. All right, so if I put 1 in there, I'll have 1 times 1 plus 4 plus 2 times 1 plus 4. That's going to be 1 times 5 plus 2 times 5. And that's going to be 5 plus 10, or 15. Now what I also want to do is I also want to test it in the trinomial to see if I also get 15. So in the trinomial, all right, I'm going to put 1 in for x. So I'm just putting it into this thing, my trinomial. 1 squared plus 6 times 1 plus 8. 1 times 1 is 1. 6 times 1 is 6 plus 8. 1 plus 6 is 7 plus 8 is 15. Excellent. Again, we know something about equivalency. 2 expressions, right? This one and this one are equivalent if any value of x I choose, and I put in this one and I put in this one, if they give me the same value, right, then they are equivalent. Okay, now again, if they don't give me the same value, what I know is I've done something algebraically wrong. The 2 things aren't equivalent, or possibly I've evaluated one of the expressions incorrectly, which can happen to any of us, right? We can make an arithmetic mistake, you know, and things can just go wrong. Let's take a look at letter B, because letter B is going to be more of the focus of what we're doing today. Let's go through it. Write an equivalent expression that is in the form of a product of two binomials. Test the equivalency with x equals 1 again. All right, so this is cool. This is really more of the thrust of what we're going to get at today. So let me write down that expression again. Okay. Now, I want to look at the structure of this expression. And what I hopefully will notice, right, is that I've got this x plus 4 that's multiplying both this x and this 2. It's almost like this was the first step of a double distribution problem that I went through the other day. The question is, what would we have started with, right? We can now reverse the distributive property, right? I want to look at this x plus 4 as if it's a single thing, right? I want to treat it as if it's the GCF of this expression and this expression. And in fact, I can do so and I can factor it out. I can rewrite this as x plus 4 times x plus 2. Right? I'm going in the reverse order, right, of my double distribution. Or I'm doing the sort of the reverse of how we typically think about the distributive property, right? Normally with the distributive property, I would take the x plus 4 and I'd multiply it by the x and I'd multiply it by the 2 and I'd get this line. Here I'm just sort of going backwards, and notice what I have now is I've got the product of two binomials, right? This is a binomial, something that's got two terms. This is a binomial, also something that's got two terms. And now, this expression, and in fact even this expression should all be equivalent. So really quickly what I'd like to do is I'd like to throw x equals 1 into that expression and make sure that I also get 15. So this is sort of my final answer, but now if I test it, maybe come down here, test my product, right, with x equals 1. I'll have 1 plus 4 times 1 plus 2. That's going to give me 5 times 3, and that's going to give me 15 again. All right. So that's really going to be the focus of what we're going to be looking at today, is looking at expressions where we have a greatest common factor that is in fact a binomial. And then we're going to be looking to rewrite those by sort of going in that reverse order of the distributive property, going kind of backwards and pulling out the thing that got distributed to each term. Right? We will often want to think and treat a binomial as a single entity when it repeats in a larger expression. And let's take a look in exercise 2, do something very similar. Consider the expression n plus 4 times n minus 5 plus n plus 4 times n minus 2. Write an equivalent expression that is in the form of the product of two binomials. Test the equivalency with a value of n. Show your test. All right, so I'd like you to pause the video and see if you can extend what we did in that last problem in letter B of exercise number 1 to see if you can write this, it's a little more complicated, as the product of two binomials. Keep in mind that n plus 4 is that common factor that can be sort of factored out, if you will. Pause the video now and take a shot at it. And if you're confused about it, don't worry, we're obviously going to go over it. Okay, great. So let's do it, right? What we've got, let me write down the expression again, n plus 4 times n minus 5 plus n plus 4 times n minus 2. Now I'm going to be very careful with all of this. I really want to look at this n plus 4 as if it was like the number 7, right? If that was a 7 sitting there and a 7 sitting there, I could factor that 7 out. I'm going to do the same thing here. I've got n plus 4. Now I'm going to do a slightly larger parentheses because what I want to say, look, that is both multiplying a n minus 5 and an n minus 2. All right, let's kind of pull back for a second and take a look at this, right? All I'm saying is, right, I can reverse the distributive property because if I had this to begin with, I could take the n minus or n plus 4 and multiply it through by both of these two binomials. Now what I'd like to do is I'd like to simplify what's inside of here. Keep in mind, right, there's no number that's multiplying this, and there's no number that's multiplying this, so I can just use the associative property of addition and get rid of those parentheses, right? There's no need for them, right? Not because, or because addition is associative, right? I can just get rid of them, all right? I can now combine some like terms. I have an n and an n, that's a 2n. I've got a -5 and a -2, and that's a -7. So I claim that this simpler expression is in fact equivalent to this expression up here. And of course, one way to test that is by grabbing a random value of n. So I'd like you to pause the video now, grab some value of n, substitute it into this more complicated expression, evaluate it, substitute it into this simpler expression, evaluate it, and see if the two are equal. Pause the video now. All right, well, I don't know what you picked. It's impossible. But if I want to avoid negatives, then I probably want some positive value of n that's bigger than 5, because here I've got n minus 5, so if I chose like 1 or 2, I'd have negatives involved. Nothing wrong with that. We could go with that. But I'm going to choose n equals 6. Just make my life a little bit easier. All right, show your test. I'm gonna go with n equals 6. Again, I'd love to use the value of n you used, but I have no idea what that is because I can't read your mind. All right, n equals 6. I'm going to plug it into the original expression. And I'm going to test it. Here we go. N equals 6. I've got 6 plus 4 times 6 minus 5 plus 6 plus 4. Notice how that's repeating. Times 6 minus 2. 6 plus 4 is 10. 6 minus 5 is 1. 6 plus 4 is 10. 6 minus 2 is 4. 10 times 1 is 10. 10 times 4 is 40. Add them together, and I get 50. All right? That was with the original. Now, let's take a look. Maybe give myself a little extra space here. Let's now do n equals 4. Move my hypercube. N equals 4 into, no, it's not n equals 4. I'm sorry, it's n equals 6. N equals 6. I'm going to put that into this expression. All right, so I'll have 6 plus 4 times 2 times 6 minus 7. All right, 6 plus 4 is 10. 2 times 6 is 12 minus 7. That's going to be 10 times 5. And that is our 50 again. Okay, hopefully whatever value of n you chose, you also found that the two expressions were equal to each other. All right? Let's keep going. These problems arise quite a bit in algebra. All right? And what I mean by these problems is when we've got a complicated expression where the same binomial occurs repeatedly in different parts of the expression. And because of that, we can treat that binomial as a single thing. It's inside of parentheses. We can do that. And we can factor it out of the expression. Things get tricky, though, when there's a subtraction involved. All right? So in fact, let's go through this one together. Exercise number 3. Which of the following is equivalent to the expression x minus 3 times 2x plus 7 minus x minus 3 times x minus 4? Show the manipulations that lead to your choice. Okay, let's do this. Now we're going to play this exactly like we did the last one, okay? But that subtraction, really this one right here, not the one here or the one over here, but the one that's kind of in the middle, that subtraction really will make our lives a lot more difficult. So let's be careful about it. Here we go. All right, remember, I'm going to think about that x minus 3 as being sort of that single thing. Okay, and I'm going to factor it out, x minus 3. Be a larger parentheses here. That's going to leave me with 2x plus 7 minus x minus 4. All right, so far this looks pretty darn similar to what I had before. The difference now is that because we have subtraction instead of addition, I can remove the parentheses around this one, but when I distribute that subtraction, remember when we subtract, we can really add the opposite, right, of what we have. So we've got a positive x. When I subtract it, I'm adding a negative x. we have a -4, and when I subtract it, I have a +4. And I want to break out for a minute because this is the real key. When you subtract something that's inside of a parentheses, everything changes sign. The positive x became a negative x. The -4 became a +4. The number one mistake that students are going to make here is that they're going to do a 2x minus x, and they're going to get x, which is correct, but then they're going to do a 7 minus 4. But really what they have is 7 minus -4, which is the same as 7 plus 4. Very critical. Subtraction problems like this throw students off all the time. So let's finally finish it. We get x minus 3. We have 2x plus negative x is x. We have 7 plus 4, which is 11. We have x minus 3 times x plus 11 for choice 2. Now again, keep in mind, right, I said the major error would be like somebody says like 7 minus 4, which would have left us with x plus 3 down here, and that's choice 1. If you then took the time on this problem, let's say you made that mistake, right, and you got x minus 3 times x plus 3, and you took the time and said, well, you know what I'm going to do? I'm going to choose a value of x. I'm going to say x equals 0, x equals 1, whatever. And you plug it into this expression, then you plugged it into choice 1, what you'd find is they'd have different values, and you'd have to say to yourself, well, maybe I got the wrong one there, you know, because they don't seem equivalent in this case. All right, let's get some practice on this. It takes a little bit of work, a little bit of practice, so that's why I've got a ton of problems here. Exercise number 4. Rewrite each of the following expressions as an equivalent product of two binomials. All right, so we run the gamut in here from ones that involve only addition, ones that have like literally one step, to ones that are more complicated. So it's kind of tricky for me to know, which one should I do, which one should I not do with you. So let me start off with a real easy one. Let's do letter A together. Let's take a look at it. We've got x times x plus 5 plus 7 times x plus 5. Right? I want to just write this as the product of two binomials. So that is going to be super duper easy because that common binomial is x plus 5. And in fact, when I write that down, when I undo my distributive property, I'm going to say, well, x plus 5 did what? Well, it multiplied x, and it multiplied positive 7, and that's it. There's nothing more I have to do. You know, I mean, in many of the other ones, I had to like do a little bit of work in terms of, well, now I've got to combine some like terms. I got to be wary about subtraction, all of that. Not in that problem, right? That's simple. So in fact, letter B is very much the same. Even though there's some subtraction involved, it's still quite easy. Pause the video now, and in letter B, see if you can write that as the product of two binomials. All right, well, let's take a look. So very, very similar to the previous one. We've got x minus 2 and x minus 2. So that's that common binomial that I'm going to factor out using the distributive property. And what did x minus 2 multiply? Well, it multiplied a 3x, and it multiplied a -4. That's it. There's nothing more. We don't have to combine any like terms. That's absolutely it. Now, letter C. This one's a particularly sneaky one. So I want you to pause the video and see if you can figure that one out, because it's kind of fun and it's a little tricky. Pause the video now. All right. So in this particular problem, we have negative 2x times x plus 4 plus x plus 4. So it almost seems like it's not happening, right? That I don't have the same thing. But keep in mind, right? Addition is associative, meaning that if I've got some addition going on, and I really do, because I've got this product plus x plus 4, right? I can put parentheses around basically almost any addition I want. So I'm going to put parentheses around here. Now, mainly I do that for a visual reason. I do it so that I can see that x plus 4 in parentheses and that x plus 4 in parentheses. But there's nothing out front of this x plus 4, right? Not the way that there was something in front of this x minus 2, you know, right? There was that -4. Not like there was something in front of this x plus 5, there was a 7. But if there's no number sitting in front of that x plus 4, right? There's no number that I'm showing as multiplying it. I could always put the number 1 there because, you know, 1 times x plus 4 is just x plus 4. So I'm going to put a little 1 there. And in fact, now I can say, oh, then I'm going to take that x plus 4 factor it out, and I'm going to have then negative 2x plus 1. And that can be very, very tricky in terms of seeing that structure. But that's where we have to feel comfortable with the associative property of addition so that we can put those parentheses around that x plus 4 and then see the structure better. So now let's get into some that are more similar to the problems that we were doing where we have to do a few extra steps other than just factor that common binomial out. Now again, the ones that have addition in them are going to be fairly easy. The ones that have subtraction in them are going to be trickier because of that subtracting, distributing through the binomial. So let's do letter D and letter E again together, and then we'll have you work on letter F and letter G on your own. So letter D, let's take a look. I've got x minus 6 times x plus 3 times x plus 9 times x plus 3. Awesome, right? So what I've got with my common factor is x plus 3. I can write that down. And what is x plus 3 multiplying? Well, it's multiplying x minus 6 plus x plus 9. Now, due to the fact that what we're doing here is addition, and addition is associative, there is no need now for those parentheses inside of that larger parentheses, right? I can just look at it like this. Again, addition is associative. Those really aren't needed. And now I can combine some like terms. I've got x plus x, which is 2x. I've got negative 6 and positive 9, that's positive 3. And I just have x plus 3 times 2x plus 3. All right, and that's really easy because again, inside of here, due to that addition, really we can just say x minus 6 plus x plus 9 is 2x plus 3, and we're kind of off to the races. Watch again how the subtraction gets a little bit trickier. Let's go through that one. I've got 2x plus 1 times x minus 4 minus x plus 6 times x minus 4. All right, so we've got the x minus 4s, no big deal, right? I'm going to factor that out. Bigger parentheses here. I'm going to have 2x plus 1 that multiplied x minus 4 minus x plus 6 that multiplied x plus 4. Okay, here's now where I have to be careful about removing the parentheses. There's absolutely nothing problematic about removing the first set of parentheses because I'm really just multiplying that parentheses by 1. On the other hand, this one, remember, when I distribute that subtraction or that multiplication by negative 1, everything's going to change sign. Again, that is the major place where people are going to make a mistake. They're going to say something like 1 plus 6, and they're going to get a 7 there, where in fact they have a 1 minus 6. Okay? So we can finish this out. We'll have x minus 4. We have 2x minus x, which is x. We have 1 minus 6, which is negative 5. And we get x minus 4 times x minus 5. Awesome. So now that we've gotten a lot of practice with these, I'd like you to pause the video, try your best to do F and G. They're going to be a little bit challenging, but I think you can get through them, and then we'll revisit them and go through each step. Okay, let's do it. Letter F. All right. The common factor is 3x minus 1. Now I'd like to just pull back from this just for a moment and talk about something, right? Some students might look at this and go, yeah, but in here, the 3x minus 1 is the first thing. Here, it's the second thing. Well, keep in mind multiplication, which is what's going on between these two binomials, and what's going on between these two binomials. Multiplication is commutative. So if you're really bothered by the fact that the 3x minus 1 is sitting there and not sitting there, well, just reverse the order of the multiplication. Multiplication is commutative. It doesn't matter which order it's written down in. All right, so here we go, right? I'm going to factor that 3x minus 1 out, right? And that's being multiplied by 4x plus 5 and by x plus 8, okay? Since we only have the addition going on inside of that parentheses, I can now just remove those parentheses. And I can now combine like terms. Inside, I've got 4x plus x, which is 5x. I've got 5 plus 8, which is 13. And I get 3x minus 1 times 5x plus 13. Easy peasy. All right, letter G. Here we go. The hardest one out there because of the subtraction, and I've got kind of this funky order reversal there. X plus 9 is multiplying both of these, so I'm going to get x plus 9 times 5x plus 7 minus 2x plus 11. Okay. X plus 9. Again, nothing that's problematic about removing that set of parentheses. Now I have to distribute that subtraction. Minus 2x minus 11. Now I can combine like terms. 5x minus 2x is 3x. 7 minus 11 is negative 4. And there's our final answer. All right. This is kind of some fun manipulation in a certain way, right? All we have to do is look for that common binomial factor, right? Reverse the distributive property, take it out of the product, and then combine the two things that it was multiplying. Sometimes that combination is through addition, sometimes that combination is from subtraction. That's where we have to be a little bit more careful, and yet we can still pull it out. All right, let's do one last problem. Always be mindful of how and why you're manipulating an expression. We're going to see that in this last problem. Exercise number 5. The binomial 4n plus 1 is equal to 7 for some value of n. What is the value of the expression shown below for the same value of n? Do not solve for n in this problem. Use mindful manipulations and look for structure to help solve this problem. Okay, great. So this actually takes us back a few lessons to when we were looking for structure in expressions. Now, right, we're thinking about that like factoring and what we did before. So I'd like you to play around with this expression, given what we've been doing in this lesson. Also, given that you know that 4n plus 1 is equal to 7, see if you can figure out what the value of this expression is. Pause the video now and play around with it by doing some mindful manipulations. All right, let's go through it. Here we go. So I'm going to kind of just play around like I did in these previous problems. I'm going to take this 4n plus 1. I know the value of that, that's equal to 7, but I'm going to leave it as 4n plus 1 for right now. We'll eventually put in 7 for that 4n plus 1, but right, what do I know? I know the 4n plus 1 is multiplying the 3n plus 1, and it's multiplying an n plus 2. Okay, so far, again, all I know is the value of the 4n plus 1, that's 7. But now I can kind of do this combination inside of here. I can remove those parentheses. And I can find out that all of this, right, 3n plus n is 4n, 1 plus 2 is 3. I can figure out that that entire more complicated expression can be written as 4n plus 1 times 4n plus 3. Awesome. But how do I find its value? Well, I know that 4n plus 1 is equal to 7, right? As well, 4n plus 3 is equal to 4n plus 1 plus 2, right? That's what 4n plus 3 is equal to. It's 4n plus 1 plus 2. Right? That's just the associative property, again, of addition. Love that property. And what is that? Well, that's got to be 7 plus 2, which has got to be 9. So in other words, this entire expression must be 7 times 2 more than 7. So that's all got to be equal to 63. And it really is cool. If you took the time and you set up an equation, 4n plus 1 equals 7, and you solved it for n, I think you get n equals 3/2 or 1.5, right? Same number. If you put that into this original expression, you'd eventually find out it was equal to 63. But we can take advantage of the structure of this expression to rewrite it as the product of two binomials, and then we can use the structure of those two binomials to figure out the value of the overall expression. All right, let's wrap this up. So mostly what we did today was more work at looking at complicated algebraic expressions and seeing common binomial factors that we could then factor out of the expression by going in the reverse sort of direction of the distributive property, right? We're undistributing the binomial factor, right? And by doing that, we can often take very complicated expressions and make them much simpler. Oftentimes, those simpler expressions are in the form of a product, what we'll eventually call the factored form of an expression, right? Because it's written as a product. Again, much more work on this because it's an important skill as the course goes on. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. Until I see you again, my name is Kirk Weiler. Keep thinking and keep solving problems.